Roads are a pivotal infrastructure to our modern civilization, more like the veins of our modern economies that enable the movement of people and goods from one point to another. Many studies show a strong and a positive correlation between good road infrastructure and advanced economies, which highlights the vital importance. But of all the types of roads out there, be it flexible pavements, typically paved with asphalt concrete mixture, or rigid pavements, which are typically paved with cement concrete mixture, to even unpaved dirt roads, the foundation structure is of the utmost importance. Geotechnical engineers are then faced with the responsibility to design and implement sustainable road foundations that not only have the capacity to carry vehicle loads, but also resist environmental challenges like water erosion. My name is Chido Chashe. I talk about geotechnical engineering related topics, including but not limited to construction methods, disasters, and past, present, and future innovations in ground engineering. Please like and subscribe to the channel. With that, let's dive into the video and let's talk about road pavements geotechnics. Welcome to Geotechs with Clement. Road pavement structures typically comprise of an embankment, compacted subgrade, a subbase, a base course, and a surface course. A well-designed and properly constructed pavement structure should be well balanced in terms of how the traffic load is distributed along its layer depth and its resistance to the environmental factors. There are two main types of pavement distress or failure. The first is the structural failure, in which the collapse of the entire structure or a breakdown of one or more of the pavement components renders the pavement incapable of sustaining the loads imposed on its surface. The second type of failure is functional failure, which occurs when the pavement, due to its roughness, is unable to carry out its intended functions without causing discomfort to drivers or passengers or imposing high stresses on vehicles. The cause of these failure conditions may be due to inadequate maintenance, excessive loads, climatic and environmental conditions, poor drainage leading to poor subgrade conditions, and the disintegration of the component materials. You can see excessive rutting where the subgrade exhibits wheelpath depressions due to loading, aggregate contamination or degeneration, which is the presence of unwanted materials in the base and the subbase or the physiochemical breakdown of the aggregate over time. We have water-related failures like the subgrade pumping, drainage problems, and frost action. In other cases, it will be the soil-related failures due to the presence of swelling soils, collapsible soils, karst condition, or even liquefaction susceptible soils. And lastly, the differential settlement failure. Designing the geotechnical aspects of roads to avoid or at least minimize the above-mentioned failures during the service life of the road infrastructure is a combination of field geotechnical surveys to check the in-situ conditions of the site, laboratory tests of the borrowed materials to be used in the structural components, and the use of local and regional design standards based on the jurisdiction. The subgrade, which is the top surface of the roadbed upon which the pavement structure and the shoulders are constructed, provides a working platform for the heavy construction machinery and equipment. Furthermore, it should have enough bearing capacity to support the pavement with undue deflections that would impact the pavement's performance. For pavements constructed on grade or in cuts, typically in areas with flatlands and good natural high-strength topsoils, or in the case of paving an existing dirt road, the natural in situ soil at the site is utilized directly as the subgrade, or the upper layer of the natural soil may be compacted or stabilized to increase its strength, stiffness, and stability. However, there are special cases in which the pavement is constructed on embankment fields made from compacted borrowed materials. For example, in areas where the groundwater table is close to the surface, or areas where weak collapsible soils are on the surface. The base and the subbase are the uppermost foundation components that provides uniform and stable support for binders and surface course. The base layer typically provides the significant portion of the structural capacity in a flexible pavement system and improves the foundation stiffness for rigid pavements. The design and construction specifications for the base materials are usually more stringent than those for the lower quality subbase materials. The selection of base materials is of critical importance. To achieve a good quality base structure, the borrowed material to be used is tested in the laboratory for the volumetric, compaction, gradation, and plasticity geotechnical engineering properties. As for the volumetric characteristics, the properties of most interest in this group for pavement design and construction are the specific gravity of soil solids, which is the ratio of the weight of a given volume of soil solids at a given temperature to the weight of an equal volume of distilled water at that same temperature. The moisture content, which is expressed as the amount of water present in a quantity of soil, and the unit weight, which is the total weight divided by the total volume of the soil sample. This is followed by the compaction characteristics of the borrowed material. Soil compaction is one of the most important geotechnical concerns during the construction of pavements and related fields and embankments. Compaction improves the engineering properties of soils in many ways, including the increased elasticity stiffness, which reduces the short-term deformations during cyclic loading from traffic, decreased compressibility, which reduces the potential for excessive long-term settlement, and increased strength, which increases the bearing capacity and decreases the instability potential. Moreover, it describes the hydraulic conductivity by reducing the void ratio, which reduces the amount of water that can be held in a soil and thus helps maintain the desired strength and stiffness properties. So, compaction is usually quantified in terms of the equivalent dry unit weight of soil as a measure of the amount of solid materials present in a unit volume. This means that the higher the amount of solid materials, the stronger and more stable the soil will be. In a standard laboratory test, the highest level of compaction that can be achieved by a particular soil is determined by compacting several specimens at different water contents. The dry unit weight versus the water content can now be plotted to produce a compaction curve, with each point representing a specimen compacted at different specific water content. From this compaction curve, a maximum dry unit weight and an optimum moisture content can be deduced, which will be used to determine the thickness, the compaction effort needed, and the number of roller passes needed for each layer to achieve a well-compacted and stable pavement in the field using the borrowed pit soil materials. As for the gradation or the distribution of particle sizes within a soil, which is an essential descriptive feature of soils, it describes the soil's texture like gravel, sand, silty clay, and more. It also shows that many engineering properties like the permeability, the strength, swelling potential, and the susceptibility to frost action are closely correlated with gradation parameters. In the laboratory, the gradation is measured using two tests: a mechanical sieve analysis for the sand and coarser fractions, and a hydrometer test for silt and finer clay materials. The grain size distribution is presented as the percentage of soil finer than a given size versus the grain size, with coarser particles defined as larger than 0.75 millimeters and finer particles smaller than 0.075 millimeters. Lastly is the soil's plasticity, which describes the response of soil to changes in moisture content. You see, when adding water, soil exhibits plasticity as it changes its consistency from stiff and rigid to soft and pliable. In engineering, clays can be very plastic, while silts are only slightly plastic, and sands and gravels are considered non-plastic. Therefore, the engineering behavior of fine-grained soils is closely correlated with plasticity rather than gradation. The soil's plasticity is quantified in terms of the Atterberg limits with values that correspond to the moisture content, of which soil's consistency changes as it progressively dries from a slurry state. The liquid limit defines the transition between the liquid and the plastic state. The plastic limit defines the transition between the plastic and the semi-solid states, and the shrinkage limit defines the transition between the semi-solid to the solid state. Overall, the pavement surface course should also be adequately designed and constructed with good quality materials, whether a rigid or a flexible pavement or the combination of the two. The Portland cement or asphalt aggregate mixture should meet the design requirements and standards. There are other advanced geotechnical engineering methods that can be used to improve pavement foundation strength and stability, from the use of stone columns and micropiles to transfer loads to deeper soils, to the use of geosynthetics between structural layers to increase the shear strength and the bearing capacity. But these are topics best suited to be covered on their own in a separate video. I have been your host, Geotechnical. Please like the video if you enjoyed or found it informative, and subscribe to the channel. You can go ahead and watch my previous video on soil constitutive models. Thank you for watching.